Alright, hello everyone. We're going to continue our discussion of parametric functions today. And what I want to talk about now is how to find the length of a parametrically defined curve. Okay, why would I want to do this? I don't know. I'm crazy, I guess. So this is just tying back into arc length, something that we talked about recently. Do you remember how to find the length of a curve? If it's written as, if you have y as a function of x, how do you find the length of a curve? Correct. Use this wonderful formula where you integrate from a to b, a and b being where your endpoints of the curve are, and you're integrating the function the square root of 1 plus the derivative squared. Sometimes that's a very easy integral to calculate. Sometimes it's super hard and you just need to punch it into a calculator or a computer or something to give you a decimal representation. Okay, cool. So here's what we're going to do though. We're dealing with parametric functions, right? So how am I going to find the length of a parametrically defined curve? So I need you to recall that for a parametric function, x, my x-coordinate, is one function of t, and y, my y-coordinate, is some other function of t. Maybe the same, doesn't matter. If I use my good buddy the chain rule, then dx is going to be f prime of t times dt. That's coming from the chain rule. Which I can further write as, so f prime of t means the same thing as dx dt. It's the derivative of x with respect to t. And similarly, dy is equal to dy dt times dt. And, I mean, if you just kind of look at this, the dt's sort of look like they would just cancel out, and of course that's equal to dx, but those are not fractions. Those mean derivatives, right? It means the derivative of x with respect to t multiplied by dt. So it's a little weird, but it is true. Okay, so I'm going to use my arc length formula. That's the formula on the left here. And then what I'm doing is I'm replacing this dy with what dy is equal to. It's equal to this mess. Whoops. And then I'm replacing dx, both of these dx's, with what dx is equal to. And when you do that, you'll notice, in particular in this fraction inside of the parentheses, these dt's are going to cancel. These dt's after the fact. Not the ones in the denominator, but the dt's that you're multiplying by are going to cancel. And so inside of the radical, you're going to have a dy dt over a dx dt, and that whole thing is squared. And then this outside dx is turning into dx dt times dt. Okay, so that's just a substitution, but it's a really kind of weird-looking substitution. If you do some algebra on this, I guess just kind of trust me here. If you do a little bit of algebra here, where I guess essentially you're just noticing that if you get a common denominator inside of that square root, you're going to have a dx dt squared in the denominator, and the square root of that is, of course, just dx dt, and that's going to cancel with this dx dt outside. So this dx dt right here is going to cancel with the one that's kind of hidden there in the denominator. And so we're going to be left with the square root of dx dt squared plus dy dt squared. So this is kind of cool because we can take the derivative of each of our components individually. You know, my derivative of my x-coordinate, so f prime of t, my derivative of my y-coordinate, so g prime of t, square both of those derivatives, add them together, take a square root, and integrate from a to b, and that's how you're going to find the length of the curve. Okay, so as a quick example, let's find the length of the curve defined by this function. So r of t is given by r sine of t, r cosine of t, and t is going to be between 0 and 2 pi. Okay, so from our formula, the length of the curve is going to be the integral from 0 to 2 pi. I know my bounds because it's given to me right over here. T is going from 0 to 2 pi. The function I'm going to integrate is the square root of the x, the derivative of the x component squared. What's the derivative of r sine of t? R, by the way, is just a constant. R is some number here. It's going to be r cosine of t squared. Plus, what's the derivative of r cosine of t? It's negative r sine of t. And I'm going to square that as well. dt. Okay, does that make sense? Seem good? Cool. Alright, so this is going to be the integral from 0 to 2 pi of, let's see, inside of the square root I get r squared cosine squared of t plus r squared sine squared of t. Oh my goodness, so I can factor out an r squared, and I'm left with the sine squared plus cosine squared, which I'm pretty sure is equal to 1. So I just get r squared underneath of the square root sign. What's the square root of r squared? Oh, that's just r. Oh, this is special. So this turns into just the integral from 0 to 2 pi of r dt. What's that equal to? Well, it's the antiderivative of r is r times t, which I'm evaluating from 0 to 2 pi. And so the answer that I'm getting, I believe, is 2 pi times capital R. What does that look familiar? Where's that from? What is 2 pi times capital R looking like? Yeah, right, that's the circumference of a circle, right? This is the circumference of a circle. And what is this parametric curve representing? It is representing a circle of radius r. That's pretty cool. So here, using calculus, we've proven that the circumference of a circle is 2 pi times the radius. All right, cool. That was pretty fun. Here's another example. Let's find the length of the curve defined by r of t equals a sine of t comma b cosine of t. So this is a little different from the last one. The last one, a and b were equal to each other. They were both equal to r. So if you were to graph this parametric curve, you're actually going to get an ellipse, assuming, I guess, that a and b are positive. And so what I want to do essentially is find the circumference, for lack of a better word, of an ellipse. And so the way we do this is, of course, same formula. We get integral 0 to 2 pi, square root. The derivative of the first thing is going to be a cosine of t, which I'm going to square. And then plus the derivative of the second thing is negative b sine of t squared. And I'm going to integrate this function. Okay. And what's tough here is that, so I get a squared cosine squared plus b squared sine squared, but because a and b are not equal to each other, I can't just factor it out and be left with sine squared plus cosine squared, which is 1. So what I'd like you to do is play with this a little bit and see if you can calculate this for me. Tell me what the circumference of an ellipse is. All right, cool. Thanks for tuning in. See you soon.